Okay, is this working? Yeah, it's filming. All right. So this is the video solution for problem number 3 on the physics test for test number 3. So we're dealing with the car. Drunk driver hits a parked Jeep, which hits a van. And then it wants to know, if I pull this up, it gives you the mass of that, the coefficient of kinetic friction. It gives you the distance to the skid mark, and it wants to know the initial speed of the car in both meters per second and miles per hour. You can assume a perfectly inelastic collision, the car and the Jeep. Then use conservation of energy to account for the lifting of the Jeep. Then assume a perfectly inelastic collision with the van, and then use conservation of energy or Newton's second law to handle the skid. You'll need to work backwards to determine the speed. So, I guess the way that this is going to work here is, this is where I'm just going to kind of, I solved this and I'm just going to run you through it. So we have the car hitting the Jeep jumps up and then comes down, and then these two, which are now collided, have collided into the van, and then the van skids a little bit. So these are our knowns. The mass of the car is 1510 kilograms, mass of the Jeep is 1815, mass of the van is 2040. The Jeep raises 0.5 meters, the coefficient of kinetic friction is 0.7, and then the skid distance is 0.63 meters. So the law of conservation of energy says that the energy final has to be equal to the energy initial plus the work done on the system. So if we're going to work backwards, we're going to look at the van, the Jeep, and the car as a system. So the energy final after their skid is 0 because it won't be moving at all. So given that we have this equation, we're going to rearrange it to the energy final will be 0 after they come to a stop. And then the energy initial is going to be their kinetic energy, which is 1/2 mass total times velocity squared, minus the, or plus the work, which in this case would be minus the work because the energy is leaving the system. So it's minus the coefficient of kinetic friction times the normal force times the displacement. If we're looking at work as equaling the force times the distance it's displaced or whatever, right? So that being said, we rearrange that to normal force is the mass total times gravity because we're not sinking through the road. And then that would be equal to 0. So I'm going to rearrange that to solve for V. I'm going to find the velocity of the all three moving at the end. And the velocity is going to be equal to the square root of 2 times the coefficient of kinetic friction, mass total times the gravity times the displacement, which we know all those values. You plugged them in. Coefficient of kinetic friction is 0.7. Mass total is 58. I don't have it written down, but it'd be like, let's see, 1815 plus 1510 plus 2040. That's 5,365 times displacement. So eventually you get the velocity is 2.94 meters per second. And that's the speed of the entire mass of the cars moving after the collision. So now we're going to go with the conservation of momentum, and we're going to have an inelastic collision here. So if we go to the textbook, I don't know if this is way too in-depth or not. Maybe I shouldn't do it this way. But in terms of the masses and velocities of something, when you have the conservation of momentum, in terms of the components, the mass 1 times the velocity 1, well, actually, these are the final. So mass 1, velocity 1 final plus mass 2, velocity 2 final should be equal to the mass 1, velocity 1 initial. So the deal with the conservation of momentum is that everything, the momentum input has to equal the momentum output. And in the case of the momentum output, which momentum is the mass times the velocity of something, we have the mass of car 1, which is the drunk, 2, which is the Jeep, 3, which is the van, times their velocity, which we just calculated here, has to be equal to, in this case, this would be the collision of the van that's not moving with the Jeep and the drunk that have been moving, right? We've already taken into account their thing. So the van's velocity is 0 because it's parked, so this whole term becomes 0. And now we're going to try to find the velocity of the drunk and the Jeep when they've been moving, right? Because it has to equal this mass and velocity coming out. We know that those are the masses of all the cars combined. This is the velocity we just solved for. We know that the velocity was 0, so this term becomes 0. And then this is the mass of the drunk and the Jeep and their velocity. Rearranging to find their velocity, we get 4.7437 meters per second. And that's the speed of the drunk and the Jeep together before they hit the van. All right, are you with me? This is like frickin' rocket science, apparently. So, shit. So now we've come to that point. Now we've got to calculate the energy of the system after the collision of this frickin' fetchin' drunk with the Jeep, right? And this is before this is before they start moving, right? So we know that the energy, their kinetic energy, is equal to 1/2 times the mass, which is of the drunk and the Jeep together, times the V1 squared. Okay, this is the energy of the Jeep and the drunk hitting the van. So you come down, energy final is going to be equal to 1/2, which is the mass of the drunk and the Jeep combined, which is this, and then times their V1, which we calculated up here, which is 4.74 meters per second. You end up with 37,352.385 joules. Okay, that's the energy final of that system. Going with the same conservation that we have to find the energy that was lost in this to the jump, because that's the energy after. But we have to know that there was some energy in that jump when the drunk hit the Jeep that we lost, that just dissipated into the ground, right? That's gone. That left our system, so it's no longer in there. So we're going to look at that as the delta E. We've labeled that, or guess what I've labeled it. So we know that the energy has to be equal to the kinetic energy and the potential energy. Well, we know the kinetic energy here, and we're going to find this, right? So delta E in this case is going to be equal to the mass times the gravity times the height. And so this is our potential energy. It's going to be the mass of the Jeep times gravity and times the height. We know it went 0.5 meters. So we have 8,893.5 joules. That's our energy there. So we have to sum those because that was the energy before we lost this energy to the jump, right? So we had 46,245.885 joules, and that's equal to the kinetic energy here, which is 1/2 mass times velocity, the energy of the Jeep and the car after the hit, but before they go in the air, right? So we come down, if you rearrange this and isolate for V, you basically times this by 2, divide it by the mass of both the energy, or the Jeep and the drunk driver, which we decided was 3,325, and then square root it. You end up getting the velocity of 5.27, which is the speed before the Jeep lifts in the air, but immediately after the collision, okay? And then knowing that, we can kind of do the same conservation of momentum thing that we did before, but this time we've got the Jeep before the collision and the driver, right? So the driver had a mass and a velocity and a momentum. The Jeep had a momentum here. And we have the momentum final, which we know that their speed at the end was 5.27, and we have their mass 1 and 2 combined, which is 3,325 or whatever. So if we isolate for the velocity 1 of the driver, the drunk driver, before all this goes down, which the velocity of our Jeep parked was 0, so it had no momentum because it wasn't moving. So we isolate again for V1 in this case of the driver, and that's equal to the mass of the drunk and the Jeep times by their velocity at the end of this, divided by the mass of the driver, the drunk driver. So we get the velocity of our driver before this is 11.6 meters per second, and then converted to meter or miles per hour, you end up getting about 25.9 miles per hour. Voila. That's how it runs. So basically the gist with all this is that we use the conservation of energy and then inelastic collision, conservation of momentums in that to basically go back in time through the problem to find the speed of the driver initially. There you go.